Stand up, walk across the room. Simple, right? You just moved, obviously, undeniably. You were there, now you're here. Motion happened, except it didn't. Motion is impossible. Logically, mathematically, philosophically, impossible. You cannot move from one place to another. It's a contradiction, a paradox, an impossibility that happens anyway. And when you understand why motion is impossible, and yet why it still happens, you will see reality in a way you never imagined. Let me show you. This isn't some new discovery. This problem has haunted humanity for 2,500 years. A Greek philosopher named Zeno figured it out. He proved with perfect logic that motion cannot exist. And here's the terrifying part. Nobody has ever refuted his proof. Not in 2,500 years. The greatest mathematicians, physicists, philosophers, they've all tried. They've all failed. Zeno's paradoxes still stand. Motion is still impossible. And yet you just scratched your nose. How? That's what we're going to explore. Let me show you Zeno's first paradox, the dichotomy. You want to walk across the room. To get there, you first have to get halfway there. Obvious, right? You can't reach the end without passing the middle. So you walk to the halfway point. But wait, to reach the halfway point, you first have to reach the quarter point. The point halfway to the halfway point. You can't get to the middle without passing through 1/4. But to reach the quarter point, you first have to reach the 1/8 point. And to reach that, you need to reach the 1/16 point. And before that, the 1/32 point. Do you see what's happening? Before you can take a single step, you have to complete an infinite number of tasks. You have to reach the half, then the quarter, then the 1/8, then the 1/16. The list never ends. It goes on forever. You have to complete an infinite number of steps before you can move at all. But you can't complete an infinite number of anything. Infinity has no end. You can never finish. Therefore, you can never start moving. Therefore, motion is impossible. You're stuck forever, right where you are. But wait, it gets worse. Let's say somehow you did start moving. Let's say you're walking toward the door. Zeno has another paradox for you, Achilles and the tortoise. Achilles was the fastest runner in Greek mythology. Imagine him racing a tortoise. The tortoise gets a head start. Let's say the tortoise starts 10 meters ahead. Achilles starts running. He's fast. He reaches the point where the tortoise was. But in the time it took Achilles to get there, the tortoise moved forward a little, maybe 1 meter. So the tortoise is still ahead. Achilles runs to that new point. But again, the tortoise moved forward. A smaller distance now, a few centimeters, but still ahead. Achilles reaches that point. The tortoise moves again, still ahead, always ahead. Every time Achilles reaches where the tortoise was, the tortoise has moved forward. The gap keeps shrinking, but it never becomes zero. There's always a gap, always a distance between them. Achilles can never catch the tortoise. The fastest runner in Greek mythology cannot catch a tortoise because motion is impossible. You're thinking this is nonsense. Obviously, Achilles catches the tortoise. Obviously, you can walk across the room. But can you tell me what's wrong with the logic? Where's the mistake? The argument seems perfect. Each step follows from the last. The conclusion seems unavoidable, and yet it contradicts what we see. Here's another one, the arrow paradox. Look at an arrow flying through the air. At any single instant, any frozen moment of time, where is the arrow? It's in one place. It occupies a space exactly equal to itself. At that instant, it's not moving. How can it be moving? Moving means being in different places at different times. But at one instant, there's only one place. The arrow is just there, stationary, frozen. Now consider the next instant. The arrow is in a slightly different place, also stationary at that instant. And the next instant, also stationary. Every instant, the arrow is stationary. It never moves at any instant. But time is made of instants. If the arrow isn't moving at any instant, and time is just a series of instants, then the arrow never moves. The arrow is stationary at every moment. There is no moment at which motion happens. Therefore, motion is impossible. You might think this is just word games, philosophy tricks. But here's the thing. These paradoxes reveal something deep about the nature of reality, something that physics still struggles with. The relationship between the continuous and the discrete, between the infinite and the finite, between mathematics and physical reality. Let me show you why these paradoxes are still relevant. Let's start with the mathematical response. Mathematicians say they've solved Zeno's paradoxes with calculus, the theory of infinite series. Here's how it works. Yes, you have to travel half the distance, then half of that, then half of that, an infinite series. But infinite series can have finite sums. The series 1, 2, plus 1, 4, plus 1, 8, plus 1, 1, 6, and so on adds up to exactly 1, not infinity, 1, finite. So completing infinitely many tasks is fine, as long as each task takes proportionally less time. You cover half the distance in half the time, then a quarter in a quarter of the time. The total time is finite. Problem solved. Except it's not solved. Here's why. The mathematical answer assumes you can actually complete an infinite sequence, that you can reach the end of something endless. But can you? What does it mean to finish an infinite process? The last step of an infinite series is what? There is no last step. So how do you complete it? Mathematicians say you don't need a last step. The limit of the series is the answer. As you add more terms, the sum approaches 1. It never quite reaches 1 from any finite number of terms. But the limit is 1. So the answer is 1. But this is a definition, a mathematical convention. It doesn't explain how physical motion actually completes an infinite sequence. It just defines the limit and calls it done. The physicist's response is different. Physicists say space and time are not infinitely divisible. There's a smallest unit, the Planck length, about 10 to the minus 35 meters. You can't have distances smaller than this. Space is quantized, grainy, not continuous. If space is grainy, then Zeno's paradox dissolves. You don't have to complete infinitely many steps. There's only a finite number of Planck lengths between you and the door. A huge number, but finite. You hop from one Planck unit to the next. No infinite series, no paradox. But here's the problem. We don't actually know if space is quantized. The Planck length is a theoretical construct. We've never measured anything that small. We can't. Our instruments are billions of times too crude. The Planck scale is a hypothesis, not a fact. And even if space is quantized, it raises new problems. How do you move from one Planck unit to the next? Do you teleport? Do you disappear from one point and appear at the next? What happens in between? If there is no in between, what does motion even mean? Let me show you how quantum mechanics makes this worse. In quantum mechanics, particles don't have definite positions. They exist in superposition, a smear of probability across space. The electron isn't here or there. It's everywhere and nowhere until you measure it. So when an electron moves, what's moving? If the electron doesn't have a position, how can it change position? The quantum wave function evolves. The probability distribution shifts. But is that motion, or is it something else entirely? Here's where it gets really strange. In quantum mechanics, particles can get from point A to point B without traveling through the space in between. This is quantum tunneling. A particle is on one side of a barrier, then it's on the other side. It didn't go over the barrier. It didn't go around. It just appeared on the other side. How did it get there? The honest answer is we don't know. The mathematics describes it, the experiments confirm it, but there's no classical path, no trajectory, no motion in the ordinary sense. The particle was here, now it's there. The in-between didn't happen. This is central to how the universe works. Quantum tunneling is how the sun burns. Protons in the sun's core don't have enough energy to overcome their electric repulsion. Classically, they could never fuse. But quantum mechanically, they tunnel through the barrier. They get from apart to together without crossing the distance. Nuclear fusion happens because motion, in the classical sense, doesn't happen. Let me tell you about the quantum Zeno effect. This is named after our friend Zeno, and it shows that his paradoxes are not just philosophy. They're physics. Here's how it works. Take a radioactive atom. It has a certain probability of decaying in a given time. Left alone, it will eventually decay. But now observe it. Measure it frequently. Check if it has decayed yet. What happens? The decay slows down. The more often you observe, the slower the decay. If you observe continuously, the decay stops entirely. The atom never decays. This is real. This has been measured. Observation freezes evolution. Watching something prevents it from changing. It's called the quantum Zeno effect because it's exactly like Zeno's arrow. At each instant of observation, the atom is in its current state, not decaying at that instant. And if every instant is observed, there's no time for decay to happen. Motion stops. Change stops. Observation freezes reality. The opposite also exists. The quantum anti-Zeno effect. For some systems, frequent observation accelerates change instead of stopping it. The act of looking speeds up the process. Observation doesn't just reveal reality, it creates it, it shapes it. It can freeze motion or accelerate it. Let me tell you about what physics says is actually moving. Here's a hint. It might be nothing. In quantum field theory, particles are excitations of fields. The electron is a ripple in the electron field. The photon is a ripple in the electromagnetic field. The fields are everywhere. They fill all of space. When an electron moves from here to there, does something actually travel? Or does the excitation at here disappear while an excitation at there appears? Is it the same electron or is it a new electron? If I have a wave in the ocean and the wave moves across the water doesn't travel with the wave. The water goes up and down. The wave pattern moves, but no actual water went from here to there. Is the electron like that? Is what we call motion just a pattern shifting through a field? Nothing actually going anywhere. Just the shape changing. Just the ripple propagating. The field is everywhere already. The excitation is just where the field is excited. Motion might be an illusion, a way our brains make sense of patterns changing in fields. Here's something even more disturbing. The path integral formulation of quantum mechanics. This is Feynman's greatest contribution, and it says something crazy about motion. In classical physics, a particle goes from A to B along one path. The shortest path, the quickest path, one trajectory. In quantum mechanics, according to Feynman, the particle takes all paths, every possible path, from A to B. At the same time, it goes left, it goes right, it goes up, it goes down, it goes to the moon and back, it goes backward in time. Every path, all at once. How do you get the actual behavior? You add up all the paths. Each path contributes a little. Most paths cancel each other out. The crazy paths cancel. The sensible paths reinforce. The result looks like classical motion, but underlying it is this insane sum over all possible paths. Every trajectory, every impossibility, all happening. Is this really motion? If the particle takes all paths, which path did it take? The question doesn't have an answer. The particle didn't take a path, it took all paths, superposed simultaneously. Motion in quantum mechanics is not like motion in everyday life. It's something weirder, something that our words don't quite capture. Let me tell you about time and motion. They're connected. Motion means change of position over time. No time, no motion. But what is time? Physics doesn't know. Seriously. Time is one of the biggest mysteries. We measure it. We use it in equations, but we don't know what it is. In Einstein's relativity, time is not universal. Different observers experience different times. Moving clocks tick slower. Time near gravity slows down. Time is relative, personal. Not an absolute background against which motion happens. Time is part of motion, tangled up with it. You can't separate them. At the Planck scale, time might be quantized too. Tiny chunks, minimum intervals. If time is granular, not continuous, then between the chunks, nothing happens. Time doesn't flow, it jumps from one instant to the next with nothing in between. Is that motion or is it a slideshow? Frames, not film, frozen moments that somehow seem like motion when viewed from inside. Here's a wild possibility. Some physicists think time doesn't exist fundamentally. The Wheeler-DeWitt equation, a candidate for quantum gravity, has no time in it at all. The universe doesn't evolve, doesn't change. It just is. All of history, all of the future exists together. A block universe. No motion because no time. What we experience as motion is just our consciousness moving through a static four-dimensional structure. But even that is an illusion, because our consciousness is part of the structure too. Let me tell you about the discrete versus continuous debate. This goes back to the ancient Greeks. Democritus said everything is atoms and void, discrete chunks. Aristotle said the world is continuous, infinitely divisible, no smallest part. They were both partly right and partly wrong. Matter turned out to be discrete. Atoms, particles, quanta, but space and time, we don't know. Maybe continuous, maybe discrete, maybe something we can't conceive. And the answer matters for motion. If space is continuous, Zeno's paradoxes bite hard. If discrete, they dissolve, but new problems appear. Here's the deepest issue. Mathematics and physics might not match. Mathematics allows infinite divisibility. Real numbers have infinite precision. You can always find a number between any two numbers. Mathematics is continuous, but physics might not be. The universe might be finite, discrete, computable. Mathematics might be an approximation that breaks down at some level. When we use calculus to describe motion, we're assuming continuous space and time. We're assuming mathematics matches reality. But what if it doesn't? What if the limit of a series doesn't correspond to any physical process? What if the calculus gives the right answer for the wrong reason? What if motion works completely differently at the fundamental level, and our mathematics is just a useful fiction? Let me tell you about computation and motion. Some physicists think the universe is a computer, a cellular automaton of vast computation. If so, motion is just updates. State changes in the universal program. Position at time step n. Position at time step n plus 1. Different values. No actual traversal, just the computer ticking through its algorithm. In this view, asking how you get from here to there is like asking how a character in a video game walks. The character doesn't walk. The pixels just update, frame by frame. The appearance of motion is created by the sequence of still images. Nothing moves. The illusion is perfect, but it's still an illusion. Is the universe a video game? Probably not, in any literal sense. But the analogy is interesting. What if motion is not fundamental? What if change is fundamental, and motion is a way we describe certain kinds of change? What if there's no actual traveling, just different configurations replacing each other? Let me tell you about the block universe again. In Einstein's relativity, the past, present, and future all exist. Space-time is a four-dimensional block. All events are in there. Your birth, your death, everything in between. From a God's eye view, nothing moves. The block just is, static, eternal. What we experience as motion is just our perspective. Our consciousness is at a particular point in the block. It experiences that point as now. It has memories of earlier points. It anticipates later points. This feels like motion through time. But from outside, nothing is moving. Everything already is. Every position you've ever been in, every position you'll ever be in, all exist. You're not going anywhere. You're already everywhere you'll ever be. This is disturbing. It makes motion an illusion of perspective, a quirk of consciousness. The block doesn't move. You don't move. You just exist at multiple locations in the block, and your consciousness samples these locations in a sequence that feels like motion. But the sequence is not a process. It's a structure, already complete, never changing, because change requires time, and time is just another dimension of the unchanging block. Let me tell you why motion might be impossible but still happen. Here's the deepest answer I can give you. Logic and reality might not fully match. Zeno's arguments are logically valid. The conclusions follow from the premises. But the premises might be subtly wrong. not obviously wrong, subtly. Zeno assumes space is infinitely divisible. Maybe it's not. Zeno assumes instants have zero duration. Maybe they don't. Zeno assumes motion must be composed of stationary instants. Maybe motion is fundamental, and instants are the abstraction. Here's a radical idea. Maybe motion is primary. Maybe rest is the illusion. In quantum mechanics, everything vibrates. Nothing is truly still. Absolute zero is unreachable. There's always motion, always fluctuation. Maybe motion is the natural state, and stillness is impossible, the opposite of Zeno. Not motion is impossible, but stillness is impossible. At the quantum level, particles don't sit still. They jitter. They fluctuate. The uncertainty principle guarantees this. 0-point motion. Even at absolute zero temperature, quantum motion persists. You can't stop it. The universe refuses to be still. Maybe motion doesn't need an explanation. Maybe motion is just what existence does. Maybe asking why motion is possible is like asking why existence exists. It just does. Motion is. Trying to break it into steps and instants is imposing a framework that doesn't fit. Motion is continuous in a way that defies decomposition. You can't understand a river by looking at individual drops. You can't understand motion by looking at individual instants. Let me bring this back to you. You moved. You scratched your nose. You walked across the room. You're doing it constantly. Living is moving. Every heartbeat is motion. Every thought is motion of neurons. Every breath is motion of air. And yet motion is impossible, logically, mathematically. The paradoxes remain. 2,500 years and counting. Nobody has fully resolved them. The best we have are workarounds. Calculus that defines limits without explaining completion. Quantum mechanics that dissolves particles into probability waves. Block universes that deny change altogether. You exist in this paradox. You are this paradox. A being made of impossible motion, constantly doing what can't be done, moving through a space that might be grainy or continuous or neither, through a time that might be real or emergent or illusory. Every step you take is a miracle of contradiction, a logical impossibility that happens anyway. You are walking proof that the universe doesn't obey logic, or that our logic is incomplete, or that reality is stranger than any framework we've yet devised. Motion is impossible, and you just did it again and again. And you'll keep doing it until you stop doing everything. And even then, your atoms will keep jiggling. Quantum fluctuations never cease. Here's the final thought. Maybe the impossibility of motion is a feature, not a bug. Maybe the paradoxes are pointing to something we haven't understood yet. Some revolution in physics or mathematics or philosophy that will make it all make sense. Or maybe the paradoxes are permanent. Windows into the fundamental weirdness of existence. Reminders that the universe doesn't owe us comprehensibility. You think you know what motion is. Walking, running, objects going from here to there. Simple, obvious. But under the surface, motion is impossible, and yet it happens. That contradiction is at the heart of reality, at the heart of you. Motion is impossible. Now go move, because impossible things happen all the time. That's what the universe does. It does impossible things and calls them ordinary. Welcome to reality, where the impossible is mandatory. Let me tell you something else that will shatter your understanding. The speed of motion. You think fast and slow are absolute. A car is fast. A snail is slow. But Einstein showed us speed is relative. There's no absolute motion. You can only measure motion relative to something else. Right now, you're sitting still, reading this, not moving at all. Wrong. You're spinning with the Earth at about 1,000 miles per hour at the equator. You're orbiting the Sun at 67,000 miles per hour. The Sun is orbiting the galaxy at 500,000 miles per hour. The galaxy is moving through space at millions of miles per hour. You're never still, not even close. You're hurtling through space at unimaginable speeds. You just don't notice because everything around you is moving with you. So when I say you're moving, relative to what? The ground, the sun, the galaxy, the cosmic microwave background, there's no answer. There's no universal reference frame. No absolute stillness against which all motion is measured. Motion is relative, which means in some sense motion is optional. From your perspective, you're still and the universe moves around you. That's equally valid. You never moved at all, everything else did. This connects to Zeno's paradoxes in a deep way. If there's no absolute motion, maybe motion is not what we think. Maybe motion is a relationship, a comparison between reference frames, not something that actually happens to an object. The object doesn't know it's moving. Only observers comparing reference frames see motion. Is motion real or just relational? If relational, what exactly is it? Let me tell you about the weirdest experiment in physics, the delayed choice quantum eraser. This experiment seems to show that the future can affect the past, that motion backward in time is possible. Here's how it works. Shoot a photon at two slits. If you don't measure which slit it goes through, you get an interference pattern. The photon acts like a wave, goes through both slits, interferes with itself. But if you measure which slit it goes through, the interference pattern disappears. The photon acts like a particle, goes through one slit. Now here's the twist. Make the measurement after the photon has already passed through the slits. After, logically, the measurement shouldn't affect the photon's behavior. The photon already decided, already went through the slits. But it does affect it. The measurement changes the pattern, as if the photon knew in advance whether you were going to measure. Some interpretations say the measurement sends information backward in time. The future affects the past. Motion through time in reverse. Other interpretations deny this, but the experiment is real. The results are real. Something strange is happening with causation and time and motion. Let me tell you about something called the arrow of time. Physics equations work the same forward and backward in time. Drop a ball and watch it fall. Film it. Play the film backward. A ball rising and landing in your hand. Does that violate physics? No. The equations allow it. It's just unlikely. Entropy makes the difference. The second law of thermodynamics. Disorder increases. But if the equations allow time reversal, why doesn't it happen? Why do we only remember the past? Why does cause precede effect? This is the arrow of time problem, and it's unsolved. At the fundamental level, motion forward and motion backward are equally valid, yet we only experience one direction. Something breaks the symmetry. Something chooses forward. We don't know what. Could you move backward in time? In principle, the equations allow it. You'd see entropy decrease, effects preceding causes, eggs unscrambling, cups unbreaking. You'd remember the future and anticipate the past. It sounds absurd, but physics doesn't forbid it. Physics is symmetric. Our experience is not. Why? Nobody knows. Let me tell you about particles that might move backward in time. Antimatter. Feynman proposed that a positron, the antiparticle of the electron, is just an electron moving backward in time. Same particle, same properties, just reversed in time. This isn't just poetry. The mathematics supports it. In Feynman diagrams, the tools physicists use to calculate particle interactions, antiparticles are drawn as particles moving backward in time. It makes the math work. It simplifies calculations. Is it literally true? We don't know. But it's a valid interpretation. Motion backward in time might already be happening in every atom that contains antimatter. Let me tell you about something called retrocausality, the idea that the future can influence the past. Some interpretations of quantum mechanics embrace this. The transactional interpretation says quantum events involve waves going forward in time and waves going backward in time. They meet in the middle to create reality. The handshake is atemporal, outside time. Motion in all directions of time simultaneously. This sounds like science fiction, but it solves problems. It explains quantum correlations without faster-than-light signaling. It makes the math elegant. Some serious physicists take it seriously. Motion might not have a direction, or might have all directions at once. Let me tell you about eternal motion. Perpetual motion machines are impossible. You can't get something for nothing. Energy is conserved. But wait, Quantum mechanics says particles fluctuate forever. Virtual particles pop in and out of existence eternally. Electrons never stop jiggling. At zero temperature, motion persists. Quantum motion cannot be stopped. Is this perpetual motion? Not in the sense of extracting energy, but it's motion that never stops, never slows down, never diminishes. The quantum vacuum is eternally restless. Motion at the fundamental level is permanent. You could say the universe is a perpetual motion machine, just not a useful one. Let me tell you about motion in multiple dimensions. We experience 3 dimensions of space and 1 of time. We can move freely in space. We move inevitably in time. But physics suggests there might be more dimensions. String theory requires 10 dimensions. M theory requires 11. We don't see them because they're curled up small, compactified. If extra dimensions exist, is there motion in them? When a particle moves in 3 dimensions, is it also moving in hidden dimensions? Are there directions of motion we can't perceive? Motions we undergo without knowing? The string theorists say yes. Particles vibrate in extra dimensions. The vibrations determine what kind of particle it is. Electron versus quark versus photon. Different motions in hidden dimensions. So motion might be happening in directions you can't see. You're moving right now in ways you can't experience, through dimensions that are inaccessible to your senses. How much motion is hidden? We don't know. We can't know until we find evidence for extra dimensions. If we ever do, let me tell you about the holographic principle. This is a mind-bending idea from black hole physics. It says that all the information in a 3-dimensional region can be encoded on its 2-dimensional boundary, like a hologram. The interior is a projection. If this is true, what is motion? When you move through a room, are you moving through 3 dimensions? Or are you a pattern on a 2-dimensional surface, creating the illusion of 3-dimensional motion? The holographic principle suggests depth might be emergent, not fundamental. You might be flat, dreaming you're deep. Motion in a holographic universe would be something like motion on a screen. The screen is flat, 2-dimensional, but the images create the impression of depth, of motion in 3 dimensions. The motion is real in some sense, but it's not what it appears. It's a projection, an encoding, something stranger than simple movement through space. Let me tell you about consciousness and motion. You experience motion. You see things move. You feel yourself move. But where does that experience happen? In your brain. And your brain is physical, made of particles. And those particles are quantum mechanical. Some scientists speculate that consciousness involves quantum effects, that the brain is a quantum computer. If so, the experience of motion might be a quantum phenomenon, subject to superposition, to interference, to all the weirdness of quantum mechanics. What if your experience of motion is in superposition? What if you're experiencing moving and not moving at the same time? What if the unity of your experience is an illusion created by decoherence? These are wild speculations, but they show how deep the mystery goes. Motion might not just be about objects moving. It might be about minds experiencing movement. And we don't understand minds. Let me give you one final paradox. This one is about motion at the edge of the universe. The universe is expanding. Galaxies are moving away from each other. The distant ones are receding faster than the speed of light. Wait, faster than light? Isn't that impossible? It's complicated. The galaxies aren't moving through space faster than light. Space itself is expanding. The distance between galaxies grows because there's more space appearing between them. Is that motion? The galaxies aren't going anywhere through space. Space is creating more of itself, carrying the galaxies apart. So galaxies can recede from us faster than light without violating relativity, because it's not motion in the usual sense. It's expansion, new space being created. This is legal. But what does it mean for motion? If space itself can grow, can motion even be defined? If the distance between two things can increase without either thing moving, what is distance? What is motion? The edge of the universe reveals that our concepts are limited. Motion, space, distance, time. These words work for everyday life. They break down at the edges. at the very small, at the very large, at the very fast, at the very strange. Motion is impossible, and also mandatory, and also relative, and also maybe illusory, and also possibly happening in directions we can't see, and also potentially going backward in time, and also eternally happening in the quantum vacuum, and also maybe a holographic projection, and also an experience in a possibly quantum brain. That's the truth about motion. Not simple, not obvious, not understood. A 2,500-year-old puzzle that gets stranger the more we learn. Zeno was right to be confused. We should be too. The fact that we can walk across a room is a miracle, an impossibility, a paradox made flesh. You just moved again. Congratulations. You did something impossible. You do it every moment of your life, and you never noticed how strange that is. Until now, motion is impossible. Now go live in that impossibility, because that's all any of us ever do.